We can represent complex numbers on an Argand diagram. Looks just like x and y axes, except the horizontal axis is the real axis and the y-axis is the imaginary axis. So complex numbers can be represented as a point with Cartesian coordinates in an Argand diagram. So if I put a point up here, say if I call that Z1, then Z1 is just up at I, because on the complex number plane, the vertical one goes I, 2I, 3I. But on the real one, it's just 1, 2, 3, and so on. So if I have another point, let's call it Z2. Z2 goes across 3, but up nothing. So you could really have it as plus 0I, but we can just call it 3. If I pick another point, say down here, and call that Z3, then Z3 goes across this direction to minus 1, and then it goes down to minus 2I. So that one is represented by Z3 equals minus 1 minus 2I. If I choose one more, let's say for example up here, if I call that Z4, Z4 is still across at minus 1, but this time it is up at 2I. So you'll notice that Z3 and Z4 are almost the same except for this sign here. That's the only thing that's different, so that means they are complex conjugates. And complex conjugates, Z, if one is Z, the other one is Z bar, then they're actually reflected in the real axis. Okay, if I've got a point xy on an Argand diagram, it can also be specified by polar coordinates of r and theta. R has to be greater than 0, and it's going to be the length that point A is from 0. So that will be our length r. And theta is going to be the angle that it makes with the positive x-axis. So theta is going to be the angle in there. Now, if this is the point xy, if I complete my triangle in here, then this value along here is your x-coordinate, and this value up here is your y-coordinate. From Pythagoras' theorem, we know that r is going to equal the square root of x squared plus y squared. And r is actually called the modulus. R is the modulus of that complex number z. And it's written as mod z, with the two lines there. Or if you like, mod of x plus iy. That's the same thing. And that is the square root of x squared plus y squared. So that, the way we say that is mod z. Now the angle, theta, it actually starts on the positive x-axis and it goes all the way around to pi in an anti-clockwise direction or around to negative pi in the clockwise direction. So theta goes from minus pi all the way to pi. And that's called the argument of the complex number. And we can write it as arg z. Just redrawing the triangle from the previous slide. There's my triangle there. If I have a look at what sine theta equals, that's going to equal y on r, which in turn tells me that y equals r sine theta. If I do the same thing for cos theta, that equals x on r, which tells me that x equals r cos theta. So instead of writing z equals x plus iy, I can also write it as r cos theta plus I times r sine theta. Or if you like, r out the front, cos theta plus I sine theta. There's also an abbreviation there. If you have a look at the R, the C for cos, the I for the imaginary part, S for sine, you can shorten that to be Z equals R cis theta. Let's have a look at a couple of examples. Say, for example, if I've got the complex number Z, which is 2 plus 2I. Having a look at that on the diagram, if I come across to 2 and then go up to 2I, then my point Z is there. Now, if I want to find the mod Z, that is the distance that it is from 0. So I can just use Pythagoras' theorem. Mod Z is 2 squared plus 2 squared, all under a square root sign. So that ends up being root 8 or 2 root 2. Now, theta is in here. Because with my triangle drawn there, I know that tan theta has to equal 2 over 2, which equals 1. Tan of what angle gives you 1? Pi on 4 radians. So I can rewrite Z in another way. So it is R, which is 2 root 2, outside of cos theta plus I sine theta. Or if I want to use the shorthand, R cis theta. Having a look at another example, if I've got the complex number Z, which equals minus root 3 plus I. On my diagram, if I go across to minus root 3 and then up to I, that's where my complex number is. If I have a look how far it is from 0, then mod Z is root 3 squared plus 1 squared under the square root sign, which is 2. Now, thing to be careful of here, the angle that I want is theta, which is made with the positive x-axis. But if I draw my triangle in here, the angle I've got is something different. But I'm still going to work with that angle. So tan alpha equals 1 on root 3. The tan of what angle gives you 1 on root 3? That means that alpha equals pi on 6. But I don't want pi on 6. I want theta. So theta is going to be pi minus pi on 6, which is 5 pi on 6. So the argument of Z is 5 pi on 6. And if I want to write that in mod arg form, then Z would be 2 cis 5 pi on 6. And one last example, if I've got minus 1 minus I, plotting that on my diagram, it would be there. So my distance from 0, my R mod Z, is going to be 1 squared plus 1 squared, square root, so that's root 2. Now this time my angle, starting from the positive x-axis, goes that way. So that's where theta is. But if I draw my triangle, I have alpha in there. So tan alpha, not worrying about what quadrant it's in, tan alpha is 1, so alpha equals pi on 4. So theta, coming this way, which is in the negative direction, but I stop pi on 4 before the end, is going to be minus 3 pi on 4. So therefore the argument of Z is minus 3 pi on 4. So writing it in long form, in mod arg form, Z equals root 2 times the cos of minus 3 pi on 4 plus I sine minus 3 pi on 4. You could also write that in cis form, but that's okay as well. And a different type of example, what if we have a complex number written in mod arg form and I want to change that into x plus iy form? It's actually very easy. The 2 is still there, But what is the cos of pi on 3? Cos of pi on 3 is a half, plus I, and what is the sine of pi on 3? That is root 3 on 2. The 2's cancel, so I'm left with 1 plus root 3 I.